All right, I think it's time to get started. Welcome back. Hope you had a good weekend. Hope the screen keeps on working. Our homework is due tomorrow. I hope you had a chance to check it out. It's on the assignment is posted on the class website. It's from the textbook problems, and you should send it into Gradescope. It's due tomorrow night at midnight, like over 24 hours from now. Please let me know if you have questions. I'd be happy to help out. I can try to help by email, or we can talk on the Zoom during my office hours, or I am going to be sitting in this room for the hour before class tomorrow, just because I have two classes over here with an hour in between, and I don't want to walk all the way back to my office and go back here. So if you want to come early, chat about the homework, I'm into it. All right? Any questions about that? I hope you've had a chance to look it over. We're going to talk some more about DFAs, right? And I wanted to do that big old example with the farmer. Remember that thing? I started doing this, and maybe I will sort of fully explain myself about this example. The farmer has a goat, a cabbage, and a hyena. I think usually it's a fox, but I've changed it to hyena because I want to write the farmer, I'm going to call F, the goat is a G, the cabbage is a C, and the hyena is a H, all right? And they're all on one side of the river. They can go across the river in a boat, but the boat is not big enough for all of them, so the farmer and one other entity can cross over at a time. And the goat and the cabbage cannot be left alone on one side because they will eat each other, or the one will eat the other. And also, same goes for the goat and the hyena, cannot be left alone. All right? And so the farmer's goal is to step by step move everything from one side of the river to the other without only taking one thing at a time, and without taking without leaving these things on their own on one side. All right. And like I said, I'm going to try to put this whole thing into the context of a DFA. So the question is, what sequence of moves gets them all to the other side? And I'm going to try to encode this whole thing into strings. So I'm going to make a DFA with the alphabet. The alphabet is going to consist of letters which describe individual movements. And the letters I'm going to use are going to be H, G, C, and F, where H means that's a movement where the farmer brings the hyena over to the other side. G means the farmer brings the goat to the other side. C means brings the cabbage to the other side. And F means the farmer goes to the other side all by himself, him or herself. All right? That's what the individual letters mean. So H means take the hyena across, etc. Right? F means that F goes across alone. All right? And so a string indicates something which may or may not be a solution to the puzzle. Oops, there's no N. So this means, I'll just say it out loud. It means first the farmer brings the hyena across. Then he brings the goat back across. Then he brings the goat across again. Then he brings the cabbage back across. Then he brings the farmer, just goes by himself across. Then he brings the hyena back across. All right? This actually is not a valid solution to the problem, because if you bring the hyena across, you cannot then immediately bring the goat across, because the goat is on the other side from where you're supposed to be in order to bring the goat across. So this means what I just said, but this is not a valid solution for various reasons. Because if you, in the first step, bring the hyena across, then the farmer is not on the correct side to bring the goat across again. All right. So there are many strings you can make out of these. Some will represent valid solutions. Most of them will not. Right. They will represent either something which is illegal, just like geographically speaking, because he's on the wrong side, or maybe they would represent a sequence of events in which the goat would eat the cabbage or something like that, which is not allowed. All right. I want our DFA to accept will accept only valid solutions. All right. And I would like to be able to answer some sophisticated questions about this puzzle by just looking at the DFA. So some questions to answer. Well, you could answer a question like, is there a valid solution at all? This is not what I wanted to ask. Well, how about, what is the solution? And then furthermore, is it unique? That is to say, is there only one way to solve this puzzle? Or is there more than one way to solve the puzzle? More generally, sort of like, how many solutions are there? Or could we in some way, if there are more than one, could we somehow be able to describe all possible solutions in general? How many solutions are there? All right, these are questions that, it turns out when you make the whole DFA, actually the answers to these questions become obvious, which is nice. It's a nice way to visualize the problem. If you can stomach, it'll take us a few minutes to actually draw the whole DFA because it's kind of big. All right, anyway, let's do it. What I'm going to have is a starting state, and I outlined last time how I want to label these states. And I'm probably not going to be able to fit all the states on the screen at the same time, but I'll try my best, all right? The labels are going to be like this. So this is a state in which everybody is on the left side of the river. That line represents the river, and then the location of the letters sort of tells you where each character is. And this is the starting state. Everybody starts on the left side. And somewhere deep down in this diagram is going to be an accepting state where everybody's on the other side. And that's actually the only accepting state. That's the only way that the puzzle will be solved. All right. This is going to be a DFA, so I need outgoing arrows with each label on them. So I need a F, a H, a G, and a C, all going outwards. Now, most of these will immediately lead to an invalid solution. For example, F, I'm going to have a special state. All the states are going to look like that one that I drew up there, except for this one, which I'm just going to call fail. And F from the beginning is a failure. Why is that a failure? F, remember, represents the farmer goes across by himself. Yeah. Then the farmer has violated the first rule of Fight Club, which is don't leave the hyena and the goat together, or the goat and the cabbage together. So that's not allowed for the solution. So this F from the first state goes to a failure, and this is like a permanent failure state. Once you get it, once you go there, it's gonna be a failure no matter what you do. All right. Are there legal moves? Actually, H from this state here, doing H is also illegal because you still have the farmer is going to leave the goat and the cabbage. So actually this is also illegal. I think the G is legal. The C is illegal. Yeah, so I'm going to put C, F, H are all going to fail from there. G is legal. All right. At least so far, it looks to me like maybe there is really only one possible solution because there's only one way you can go that's not a failure, at least from the beginning. Maybe there's going to be branchings later on. But anyway, after the farmer goes across with the G, what it looks like now is H and C on the left and F and G on the right. Right? And now I'm going to try and do the same things. Think through all possible letters here, and then see which ones are a failure from here, which ones are actually legal. Let's just talk, maybe we'll just go alphabetical order here. C, is C allowed from this? No, you can't do C because C is on the wrong side, so that's a failure. Oops, C. Is the F allowed? Yes, I think the F is allowed, and that will, you got to ask yourself, if I do F, does it lead to one of the already existing states, or do I need to draw a new one? I think I need to draw a new one. If I do F, the F will go back to the other side, and everything else will be fine. So I'm going to put that up here. F, H, C, and G on the right. All right. Now there's going to be more arrows out from that one, but let's just finish off this this state right here. Finish drawing more arrows here. I did F and C. How about H? Is H legal here? No. H is on the wrong side, so H is a failure. And how about G? Yeah, G actually is legal. It's not really a useful step in terms of solving the puzzle, but it is allowed for the farmer to go back, and it will go back to the starting state if you do G there, right? Take the goat back across. Okay. Great. That's my next state. Okay. Everybody with it so far? Oh, we just gotta. So my strategy is just from every state, figure out which arrows are legal. If they are legal, make new states as needed, right? As we go. So from here, again, let's just do alphabetical order. Is C allowed here? I think it is. You can bring the C over to the other side. So now I happen to know there's going to be two new states coming out of this one. So I'm going to put the C. I'll move the C on this side. All right, and then it looks like H alone on the left side and everybody else on the right side. All right. Let's continue with the arrows up here. That was a C. Is F allowed from this state? I think yes, it is. The F goes across by itself. Does that make a new state? No, it goes back to this state. So. In fact, if you think about the way that this puzzle works, actually every arrow on the diagram is sort of reversible with the same label, apart from the failure arrows. So actually, would you mind if I just fill this in? You can always, in this diagram, you can always just go back the step that you came, except for the failure arrows. All right. Okay, also from this state here, I did F and C. What about G? G is not allowed from here because the G is on the wrong side of the river, so that's a failure. The H is allowed, and the H will actually go to a new state with a return arrow. And the H will go F, G, H, and C on the left. Right? Okay, so we do have a bit of a branching path here. There still might be only one way to get to the correct answer, but we do have two paths at least at this point. All right, let's just continue. How about I'll continue down the left branch of this path here. I think the only legal move here would be G, right? You can't go back alone because the G and the C will be left, and you can't do the C. Oh, no, C is legal, it just goes back here. So the only interesting legal move is G. And that will end up with this, FH, and then, sorry, FCH, and then G on the right side. What? That's not right. FGH on the left. Sorry. FGH on the left and C on the right. Okay. With a G going in the reverse direction. From this state, H is illegal and also F is illegal. So those are going to be failure arrows. H and F are both illegal there. All right. And let's go to the one on the far right there. Similarly, there's only one. Is there only one legal move here? Yeah. Okay. So there's the H, which the H which just goes back here. You can also do G here, and if you do G, it will have F, G, C on the left and H on the right. And you can go backwards with the G. All right, and then we also have a failure arrow there with a C and a F, right? Those are failures from that state. Unfortunately, in my diagram, I'm going to have to cross the streams a little bit. I don't like doing that, but you mind if I just go sort of right through there? This is F and C, right? C is just illegal. If you do F, then the high unit needs to go. All right. Okay, let's keep it going here. I'm gonna have to scroll off the top of the page here soon, but it doesn't really matter. How about from this state at the far right? What can I do from here? I can do G and it goes up, or I can do C. F is a failure and H is a failure. So I'm gonna say here F and H are failures, but I could do C, which ends up looking like G alone on the left, and then F, H, C. And there's a C going back like that. All right. And I think that handles this state. From this state here, I can do F is a failure, C is a failure. But I could do H, right? H brings the H across, leaving G on the left and everybody else on the right. And actually that's the same as this state. So these two branches actually are coming back together at this point. All right. We getting anywhere here? Maybe. Let's just keep going here. I mean, when you're doing this, hopefully you don't just keep on generating new states forever. I mean, it's not going to be forever. We're actually almost done here. From this state right here, what is allowed? The F can go across by itself. That is allowed. Or you could do H and C, which already have arrows. G is illegal here because G is on the wrong side. So G is a failure, but F is allowed. And that leads to FG on the left, HC on the right. And of course you can go backwards to that F. All right, we're almost done here. This state here, FGHC, if you do G, actually that sends you to the victory state. Maybe I'm going to put it like over here just so that it fits in better. FGHC, right? And from that state, H and C are illegal. All right. And we're pretty much done at this point, although you need, from your accepting state, you still need outgoing arrows with every label on them. So the G here can go back. C is not allowed because you leave the G and the H together. H is not allowed because you leave the G and the C together. And F is not allowed because you leave everybody together. So actually everything else from here is a failure. F, G, H is a failure. Not G, C, H. All right. This is my final answer then. That's the big diagram. It's big, yeah. I hope you didn't start halfway down the page. I should have said, start this on a new page. All right. This is, I think, the biggest DFA that we're going to do. We're going to talk about this semester. Could we answer the questions that I had asked at the beginning? Is there only one solution? What do you say? No, actually, I think you can, if you can hold in your mind the flow of the arrows here, what I see is a solution would represent some kind of path from here down to here, right? And I can see basically two different, like really substantially different ways of doing that. You could go that way, or you could go sort of round the bend the other way, right? And these are, I want blue. Blue. I could also do this. The red one or the blue one, right? These are two substantially different ways that you can solve the puzzle, and they're not the same as each other. All right. So, as for the question, is there a unique solution? No, there isn't. Yeah.
Is most of count going backwards or just
Yeah, I was going to say, are there still yet other solutions? Yeah. So there's many actually sort of stupid ways that you could do this. For example, I'll do another blue one. How about, instead of that blue one, how about this? Start up here, and then you go around like this. You can go around that loopity-loop as many times as you like. And that's still a legal solution, right? It's not a practical solution, but it is still a legal solution by going around that loop. Or, if you wanted to be even stupider, I think you already have this in your mind. Those of you who are especially stupid, you could just go like back and forth here a whole bunch of times, and then go through, right? There are many ways that you can solve this in stupid ways by doing loops, either big loops or really small loops. So, I will say, I'm going to undo all of those scribbles. I will say, just to answer the questions that I had before, I will say there's sort of two, quote unquote, sort of good solutions. And I will say, what I mean by good, actually I can say, I don't really mean that in a formal way, but you could say, formally speaking, what I mean by good solutions would be like shortest length, right? There are two solutions which take the fewest possible steps. And there are many other solutions which just do stupid extra steps, but they're still valid solutions. So there's sort of two good shortest length solutions. Many, in fact, would you mind if I say, infinitely many other solutions which are going around loops, which are, in terms of the original puzzle, they are not practical solutions. They're not really interesting other solutions, but there are infinitely other solutions. All right. Excellent. So this is kind of the power of DFAs to model interesting scenarios. This is a kind of not a terribly realistic scenario, but it's interesting, and you can use the diagram. Once you draw the diagram, it's sort of like the diagram is good enough to actually be able to answer pretty much any question that you would like to be able to answer for this interesting puzzle. All right, and many other kinds of puzzles can be modeled by DFAs. I don't want to do other examples, but we could do a similar kind of DFA. We could make a DFA, for example, for winning at tic-tac-toe, right? It would look something like the starting state is like that, and then there are several arrows going out of this. You could go to here, or you could go to here, or you could go to just ignoring symmetries of the board. These are basically the only possible 3 starting moves. And then you could have arrows from each of these to where the possible other move would be, right? And you could in theory draw a whole diagram. It would be very big in this example. And then you could use that diagram to decide what your best move would be. Now, it's not always possible to win at tic-tac-toe. You're usually going to get a tie, but the same idea is true, though. You could draw a giant DFA to try to answer sophisticated questions about the puzzle. You have a question?
Yeah, just for back to the farmer.
Yeah, sure.
Example, to write the string for that, do you just follow the arrow of like the accepted?
Yeah. So maybe that's a good idea to write. Can we write like actually what the accepted strings would be? I mean, there's infinitely many, but as far as sort of the 2 good ones, they would be following the arrows from top to bottom. G, F, C, G, H, F, G would be, that's the left side. Sorry, I can't keep it all on the screen at once. But the accepted sort of good solutions, the first one would be G, F, C, G, H, F, G, right? That's the one which goes around the path to the left. And the one which goes around the path to the left would be G, F, H, G, C, F, G. Yeah, thanks for that. That's a good idea to write in. These are the 2 good solutions. And those 2, they are the shortest strings which are accepted by the DFA in that example. Any string shorter than that is an automatic failure. There are many other failures too. All right. I just had another example of something you could, in theory, do with a DFA, but you wouldn't. I mean, a tic-tac-toe is not that complicated. A DFA would be quite large. You could also do this one. You really would not want to do, practically speaking, something like a Rubik's cube. A Rubik's cube has only finitely many configurations that it can be in, although it's very, very many. And from each configuration, there's only finitely many possible moves you can do. Again, it's kind of a lot, but there are only finitely many. So in theory, you could make an extremely large DFA, and then whenever you wanted to solve your Rubik's cube, you just follow the arrows to the accepting state. This is not really practical to do.
So is the Rubik's cube finite or infinite?
It's finite. It has, you know what I mean, the Rubik's cube? Yeah, it has.
Technically, there are infinite numbers.
No.
If you would just turn it and turn it back. Would it be that infinite?
There's finitely many configurations it can be in. Yeah, the possible number of so in the DFA you have one state for every configuration and arrows for every kind of move you can make. You could do infinitely many different paths throughout the DFA, but
I was talking about the string.
yeah, the amount of legal strings would be infinite. Yep. All right. So all of this to say, DFAs in theory can be used to model actually very sophisticated things. Usually we're going to think of DFA as like the simplest possible kind of computing machine, but a DFA, I mean, yes, they're simple, but they are capable of solving Rubik's Cube, which is better than I can do. Like I kind of know how to. I memorized the steps to do, but I've forgotten by now. And my kid just last week said, "Hey, can you teach me how to do the Rubik's Cube?" And I said, "Yeah, I used to know how to do that," and I quickly realized that I no longer know how to do it. But it's not that hard if you just have to memorize a bunch of steps. You might say, "Why don't you just memorize the whole DFA?" Well, you could. It's too big, that's why. All right. Any thoughts about that? So, no more giant examples like that. I just wanted to sort of inspire your mind that DFAs can be used to model lots of very complex phenomena, even though they're kind of simple. I want to try to answer another type of question here. And actually, there's some questions on the homework of this format. Usually what we've done so far is I describe a language and then we build a DFA to achieve that language. But you can also go the other way around. I show you a DFA and you tell me what is the set of strings which are accepted. So here's an example like that. Look at this DFA and tell me what strings are accepted or rejected. Let's just talk about what strings would be accepted here. Now, maybe you can tell me, I would like, in general, like a simple explanation or description of the set of strings which are acceptable. If you can't just look at this and immediately say so, you might want to just try to write out some examples. Like, I would say, first of all, the empty string is accepted here because you begin in the accepting state. We could also say A is accepted. B is accepted, right? Something like A is accepted because that's all that. Or I could do many B's, that would be accepted. B. How about not accepted?
ABA.
Yeah, somebody said BA or ABA. Maybe I would suggest like try a bunch of examples to sort of get a feel for it. Anyone want to try to, can you describe in words what this is? Yeah.
I can describe what it's not. Like,
Okay.
you can't end with an A for strings longer than 2. No.
Can't end with an A or have strings longer than
No,
2.
4 strings that are longer than 2. Like, if it's longer than 2, then it can't end with an A.
Okay. But otherwise,
It can end with an A. It's like A.
Yeah, but I think some things which are longer than 2 also.
Right, you're right.
Yeah, there's a better way to say it than that. You know,
All A's have to be before all B's.
yes, all the A's are before all the B's. Is that what you said? Yeah, yeah. All the A's are before all the B's. I think that's this except when all A's are before all B's. Anyone want to try to write that as a set? Accepts the set. I'm going to write something with like A's and B's with exponents maybe. Huh? Yeah, go ahead.
A to the n times b to the n.
Yeah, I like that. So I'm going to put,
M.
yeah, put 2 different letters up there. If you put A to the n, B to the n, it means they have to be the same number of A's and B's, which actually is not true of this DFA. A to the n, B to the m. Sorry, I scrolled away from the picture. I'll bring it down there also. Now, in our book, when they just write exponents and don't tell you anything about them, you assume that the exponents are natural numbers, which means they can be 0, 1, 2, 3. Are these allowed to be anything, the n and the m, or do they have to be? I think actually, can they be anything? Yeah, I think they can. I don't know. For some reason, I wrote on my paper that they could be anything. So I will say n and m greater than or equal to 0, something like that. Although in our book, usually they would leave that out. Just when you see exponents, they can be anything. I don't know why I wrote it differently on my paper, but I think this is the right answer. All right, it accepts the string a to the n, b to the m. As you probably have discovered, there are many ways to say this answer. This I think is maybe one of the best ways to say it, the simplest ways. Although, like he said, any string in which all the a's happen before all the b's, that's also correct. Although this I think is a clearer way of saying the same thing. Yeah.
Wouldn't they have to be integers? Because could you
Oh
have, like,
yes.
half of an n?
Yeah, there's no such thing as exponents
Okay.
which are not
I didn't know if you were
integers.
to say that.
Yeah. No, in this class we don't say that. This whole semester we are never ever going to discuss anything that's not an integer. So, yeah. Okay, great. Oh yeah, my terminology here. This set is called. I think I said this last time. The language accepted by the DFA. All right. And we write this for a DFA M. If the DFA has a name, M, the language is written L of M, the language of the DFA. All right, I think I said this last time. A big question that we're going to be asking ourselves, big question, which sets can be the language of a DFA? All right? If I just invented a set out of nowhere and said, find me a DFA which has this set as its language, is that even possible for every set? Like, for which sets can you actually do that or not? Actually, we've already talked about this using different terminology. It's not always possible. So for example, this set, let's say a to the n such that n is prime. This is an example that I mentioned a couple times ago. Actually, this has no DFA, right? Because a DFA is not sophisticated enough to be able to measure if a number is a prime number or not. So this actually has no DFA. And there are even simpler types of examples of sets for which you cannot make a DFA to accept just that set, right? That set there actually has no DFA. So there's a word for a set which can be accepted by a DFA. Such a set, I mean, they're called languages. Here's a definition. A language that is set is called regular if it is the language of some DFA. All right.
Isn't it a set? It's called
Yes, a language is a set of strings. That's what the word language means. It means a set. So, yeah, when I say language, it means set. It's the same thing. So a language is called regular if it is the language of some DFA. And so that big question which I asked a few moments ago, I said big question, which sets can be the language of a DFA? Another way of saying that same question is, which languages are regular? All right? If I give you a language, can you tell me whether or not it's a regular language? Which languages are regular? All right, and this actually is another way of asking the basic larger question of like, what are the computational capabilities of a DFA? Like when I say a DFA is not sophisticated enough to tell if a number is prime or not, that's equivalent to saying that this is not a regular language. All right, and so all of this, the theory of computation, you know, the course is called the theory of computation, but our book is called languages, right? What's the title of the book? Well, languages. Formal languages. Yeah, sorry, I forgot the title of the book. It's languages. What really they are the same topic though. It's just a different way of phrasing it. I typically think of this course as being about different types of machines. You could just as easily say this course is about different types of languages. There's languages of a DFA. There's also languages of a Turing machine. There's languages of other kinds of things. So our textbook is written sort of exclusively from the point of view of languages. Everything's about languages. Usually we're going to describe things in terms of machines, but it's the same as talking about different types of languages. All right, which languages are regular? Well, if I give you a language and ask you if it's regular or not, so you know, there are two options. You can either try to show it is regular or show it's not regular. So to show a language is regular, you must remember regular means it is the language accepted by some DFA. To show that some language is regular, you must actually build the DFA which accepts it. Right? To show a language is not regular, this is much, much harder. You have to somehow prove that no possible DFA can accept this language. And at this point in the course, it's not clear how you would ever do that, although we are going to talk eventually about techniques for doing this. But to show a language is not regular, we must somehow prove no possible DFA can accept it. And I will just say parenthetically, this is much harder. And we're not even going to try to do this for a couple weeks. Eventually we will talk about a specific method for doing this, which works sometimes. In general, this is a hard question to try to figure out. All right, we got 10 minutes left. I have one last example of a DFA. which is more interesting than the other ones that we've talked about so far. I really would like to try to think of the DFA more like a computing instrument, which is actually determining some kind of useful mathematical thing. So I would like to do a fancy DFA, although the idea is fancy, although the actual DFA when you write it down is going to end up being fairly simple. A fancy DFA for binary numbers. So my alphabet is going to be 0, 1. So instead of A's and B's here, I'm going to use strings of zeros and ones. But those strings I will interpret as numbers, not as, text strings or whatever. For binary numbers, and I want to accept when the number is divisible by 3. This is a computational problem which I think is hard even for a human being to do. If you show me a number written in base 10 and ask me if it's divisible by 3, I can pretty much figure it out because I know some tricks about divisibility testing for numbers which are divisible by 3. But here I want to do this in binary, which to me is much harder because I'm basically unfamiliar with the binary numbers. I mean, I know how to work with them, but I'm not used to doing divisibility things with binary numbers. But anyway, I thought maybe let's just refresh our memory about binary numbers. You want to hear a math joke? There's 10 kinds of mathematicians, the ones who understand binary and the ones who don't. You get it? I don't really like math jokes in general. I think they're sort of elitist. I feel like the whole point of a math joke sometimes is like to impress people with how smart you are. Like that joke that I just said. Part of what's funny about it is the knowledge in the back of your mind. Like, my idiot roommate probably wouldn't get that joke, but I do get that joke because I'm smarter than those idiots who don't get that joke. Not because the joke is actually funny on its own, but because it makes you feel smart. I don't really like that. Anyway, the binary, so this is the way that decimal is the ordinary way of writing numbers, base 10. The binary is using using only ones and zeros. So the way you count for 0 and 1, they look the same. But the decimal number 2 in binary is written as 1 followed by 0. 3 would be 1, 1. 4 would be 1, 0, 0. The idea is when you count in binary, you count in the way that we usually do, only you carry over to the next digit like immediately, because you're only ever allowed to use zeros and ones. So the next number here would be 101, then 110, then 111, 101, sorry, 1000. I'll just write up to maybe 11. I'm going to try and line these up. So 5 is 101, 6 is 110, 7 is that, this is 8. I'll go up to 12, say. I hope that you've seen this before. One, 100. All right? These are decimal numbers and their binary equivalents up to 12 at least. Now, I want to make a DFA which reads one of these binary numbers and tells you if it is divisible by 3 or not. So the ones which are divisible by 3 would be here, here, here. I'm just circling the multiples of 3. And what our DFA is going to do is it's going to read those as strings from left to right and tell you if it's divisible by 3 or not. This, to me, as a computational problem, seems kind of intensive. Especially the fact that you have to read one letter at a time starting on the left. That is ordinarily not the way that you read a number, right? If I want, especially if you're talking about these divisibility tests, usually you look at the rightmost digits and do some kind of little trick or something. On the right, not on the left. This DFA is going to read those strings from left to right and tell you if they're divisible by 3. Anybody see an obvious pattern of these things? Yeah?
The leftmost is always a 1. Oh wait, no, never mind, not the 0.
Well, this is generally a fact about all numbers. The leftmost digit is always going to be a 1, just because we never write a number which has a zeros on the left digit, unless it's just the number 0.
Oh, right.
But yeah, all of these numbers actually begin with 1. Whoa,
Or
sorry.
the last digit is alternating between 0 and 0 and 1.
Okay, that's true. Does that help you to know, if I just give you a big number, say, can you tell me, is that divisible by 3 or not? The answer is, I have no idea really. But actually, I'm here to tell you, I don't know if we'll get it done in 5 minutes. There's a DFA which can read that string from left to right and tell you if it's divisible by 3 or not. And you can do this only using 3 states. Can you believe it? It's an impressive kind of thing, in my opinion. Yeah. Do you know how to do it?
I was thinking that it could be something with the number of digits that are 1. Like, with the exception of 0, there's always only 2 digits that are 1.
I don't think that's true. Yeah, I mean, I think that's only because I only wrote so many here. If you continue down the list, 18 has 3 ones. Yeah, you're gonna get lots of 1s if you go down the list far enough. Yeah. I actually don't know off the top of my head if what I just wrote is divisible by 3 or not, but if you make this DFA, you can easily check any of them. So maybe we're not going to get to the end here, but I want to talk about some basic ideas that are going to help us to build the machine here. Yeah, what I would like to think about is DFA reads from left to right, of course, as always. I would like to know, how does the value of the string change when we encounter a new letter that is a new digit on the right? For example, if I start with 101, now there are sort of 2 different ways you could extend this, right? You could add a 0 on the end, or you could add a 1 on the end, all right? This is how the DFA is going to have to work. It will be in a particular state for the number that it's read so far, and then it's going to read another digit, which is either a 0 or a 1, and it has to decide how to switch states from there. I would like to try to say, can we say, how does the value of the string change when we encounter a new letter on the right? It could be either a 0 on the right or a 1 on the right. So there's 2 options, right? When we when we have, let's say, some number x and put a 0 on the right, the value becomes, anybody have thoughts about this? This is like, for example, on this chart here, if I went from 1-1 and turned it into 110, this 1-1 is in decimal 3, 110 is 6. It doubles, yeah. Why should that be true? Can you say something about why does it double? Because it's binary. Yeah, what you're doing is you're shifting the digits all to the left, basically, which in base 10 numbers, that is that's what happens when you multiply by 10, right? You stick a new 0 on the end. That indicates that you have increased the place value of all the other digits, and that's because you multiply it by 10. Doing the same thing in binary has the effect of multiplying by 2. So when we have an x, we put a 0 on the right, the value becomes 2x. All right? And what if we put a 1 on the right? This is slightly more complicated to describe, but when we have an x and put a 1 on the right, yeah, it becomes 2x plus 1, right? Because putting a 1 on the right is the same as putting a 0 on the right and then adding 1 extra. And putting on 0 on the right is multiplying by 2, and then you add 1 extra. So it looks like 2x plus 1 if you put a 1 on the right. This is the very basis of how we're going to reason about the DFA. We start in a particular state, and then from that state, adding a 0 multiplies by 2. Adding a 1 multiply by 2, and then adds 1, all right? Maybe we'll have to stop at this point, but we're going to turn this into a DFA next time. All right, see you all then. Check out the homework. Let me know if you have questions. I can try to help by email, or we can chat on Zoom.